Hello, my name is John Cody. I'm an engineer from Vancouver, Canada. Today we'll be continuing our proof of the quadrea of the projective quadrangle theorem in universal hyperbolic geometry. The setting is, here we have a projective plane in universal hyperbolic geometry with the null circle and projective points A1, A2, A3, and A4. Side quadrants is Q1, Q2, Q3, Q4, and spreads S1, S2, S3, S4. Last time we showed that the quadrea of the projective quadrangle is given by these two quadratic equations in A. We proved that these two quadratic equations are compatible and that they have a common solution given by this expression right here. In this video, we'll be continuing on with the proof. What we'll be doing is substituting this expression for A back into the second quadratic equation, number 2, and showing that this equation is valid, that the left-hand side, A minus Q1, Q4, S1 minus Q2, Q3, S3, all of that squared is equal to 4 times Q1, Q2, Q3, Q4 times 1 minus S2 times 1 minus S4. In part 1, we made use of the quadratic compatibility theorem, which is theorem 1 in the book Divine Proportions by Norman Wildberger. That theorem stated that the two quadratic equations x minus p1 squared equals r1 and x minus p2 squared equals r2 are compatible precisely when p1 minus p2 squared minus r1 plus r2, all of this squared is equal to 4 times r1 times r2. And in this case, if this is true, then if P1 and P2 are not equal, so that you don't get a 0 in the denominator here, then there is a unique common solution x. And we'll do the same thing as last time in part 1. We're going to create this expression in Mathematica, create a function in Mathematica we'll pass in the variables P1, R1, P2, and R2. And this is the definition of this function, and it matches the definition in the quadratic compatibility theorem. Next, we will compute the quantity A, the quadrea of the projective quadrangle, by replacing P1, R1, P2, and R2 with the quantities from these two equations, equation 1 and equation 2. So this is this quantity here, Q1, Q2, S2 plus Q3, Q4, S4, that's P1. This right-hand side is R1. This right-hand side is R2, and the quantity Q1, Q4, S1 plus Q2, Q3, S3, that is P2. So when we substitute that in, we get into our equation for x, we get the expression for the quadrea of the projective quadrangle. Okay, so what I'll do is I'll restate the quadrea of the projective quadrangle theorem, which says, suppose A1, A2, A3, and A4 are distinct projective points with quadrants Q1, the quadrants between A1 and A2, Q2, the quadrants between A2 and A3, Q3, the quadrants between A3 and A4, and Q4, the quadrants between A4 and A1, and spreads, S1 is the spread between the line A4, A1 and the line A1, A2. S2 is the spread between lines A1, A2 and A2, A3. S3 is the spread between line A2, A3 and line A3, A4. And S4 is the spread between line A3, A4 and line A4, A1. And suppose we also have the quadrea A. Then this theorem states that the quadrea of the projective quadrangle is the common solution of the following pair of quadratic equations. And these are their two quadratic equations. last time we proved that they are compatible. So again, we're going to substitute the value we have for A into this equation 2, and then prove that the left-hand side is equal to the right-hand side. And we'll be using we'll do this algebraically, and we're going to be using Mathematica functions, expand, factor, together, numerator, denominator to perform algebraic manipulations. Okay, so the left-hand side of this equation is given here. Left-hand side, LHS, is equal to A minus Q1, Q4, S1, minus Q2, Q3, S3. All of that squared. And here it is here. Next, we're going to expand. We're going to use the Mathematica function expand to expand out the left-hand side. And we get this expression in terms of the quadrants and spreads. This long expression when we expand that out. Next, for this long expression we just expanded out, we're going to put it over a common denominator, all the terms over a common denominator, so that we're going to use the together function from Mathematica to do that. And when we do that, call that function together on our left-hand side expanded function up here, we get this left-hand side expanded together variable. And here it is here. It all expands into this quantity. And here's the common denominator down here. So we're going to grab the numerator and the denominator from this above expression. So we're going to call the numerator function on left-hand side expanded together. And the denominator, we're going to call the denominator function on that. And here's the result of the denominator function call. Okay, now we'll look now at the right-hand side of our quadratic equation number 2, and that's given as 4 times Q1, Q2, Q3, Q4 times 1 minus S2 times 1 minus S4. The denominator of this is 1. And then what we're going to do is bring up the denominator from the left-hand side and multiply it on the right-hand side. So right-hand side multiplied by the left-hand side denominator is this quantity right here. And then we're going to expand this quantity out, and that gives us this result here. And finally, so we're going to subtract the left-hand side numerator from our expanded right-hand side multiplied by the left-hand side denominator, and we get this long expression. Okay, next what we're going to be doing is computing the quadrants and the spreads from the points, our projective points A1, A2, A3, A4. So projective point A1 is x1, y1, z1, A2 is x2, y2, z2, A3 is x3, y3, z3, and A4 is x4, y4, z4. Next, we'll define our 3 functions, the join of 2 projective points, which gives a line, the quadrants between 2 projective points, and the spread between 2 projective lines. So we will call the quadrants function with, to get Q1, we call this quadrants function with projective points A1 and A2. Q2 is the quadrants between A2 and A3. Q3 is the quadrants between A3 and A4. And Q4 is the quadrants between A4 and A1. And when we do that, we get these four quantities. This is Q1 in terms of x1, y1, and z1, and x2, y2, and z2. This is Q2 in terms of the projective points A2, A3, the x, y, z's of those 2 points. Similarly, Q3 is given by this expression here, and Q4 is this expression. Next, we'll compute the line lines L1, L2, L3, L4 by calling the join function of the projective points. So L1 is the join of A1 and A2, L2 is the join of A2 and A3, L3 is the join of A3 and A4, and L4 is the join of A4 and A1. And we get these 4 lines. This is L1, L2, L3, and L4. Finally, we'll compute the spreads between the lines. So S1 is the spread between L4 and L1, S2 is the spread between L1 and L2, S3 is the spread between L2 and L3, and S4 is the spread between L3 and L4. And these are the quantities here. So this one is S1, this one quantity here is S2, this quantity here is S3, and finally this quantity here is S4. So we've computed the quadrances and spreads of the x, y's, and z's, and when we substitute that into our left-hand side minus the right-hand side, this long expression here, each one of these q's and these quadrances and spreads, we're going to substitute in the expressions in terms of the x, y's, and z's, and then factor that all out. And when we do that, we get the result that when we factor it, the result is that we get 0, meaning the left-hand side minus the right-hand side is equal to 0. And that's what we were after when we started out here. We substituted into this equation 2, and we expanded the left-hand side and the right-hand side, and then we substituted the quantities of the quadrances and spreads in terms of the x and the y's and the z's, the projective points. And when we expanded that out and all factored, then we got the result of 0. So that proved that indeed this equation is valid with this quantity for the quadrea A. Okay, so that's the end of the proof. So this portion of the proof covered the case when P1 is not equal to P2. So this quantity here is not equal. The sum of this and this is not equal to this and that. That's the condition. That way you don't get a 0 in the denominator here. Next time we'll explore what happens when these are equal. We'll see what happens then. But this is the general formula for quadrea of projective quadrangle when these quantities are not equal. Okay, thank you for listening.